All right. In class last time, we had some tech issues with the screen and whatnot, so I decided to go ahead and re-record the lecture that we had yesterday. It's going to be really short, but because I'm going to be going through this software demo that we went through in class, but there was a couple things I wanted to cover just to make sure that we had it on the record and whatnot. I'm not going to go through the announcements in great detail, other than to say all the outstanding homeworks are graded. The homework is due on Friday, which for this recording is going to be tomorrow. And then the attendance grades will be updated by the time we have class tomorrow. So with that, we're going to do our Mastan demo, but I wanted to go through the additional truss items that I discussed in class yesterday. So uh, I have Mastan pulled up here, and what I'm going to do is I'm going to file open, and I've got it navigated to the desktop, and I'm going to open the truss that we analyzed in class on Monday. So here's the truss, and we talked about things like being able to plot the deflected shape, and here you can see the deflected shape, pretty straightforward. We also talked about going to File, Create Report, and doing things like plotting, or creating a report with the reactions, or creating a report with the element results, and what have you. And the way Mastan works is it just keeps appending to that report. So I can say, okay, give me the geometry, and now it'll give me all of that. I can also hit clear text just to get rid of all of that. But I wanted to show you something that's relevant for your project. Okay, and we talked about this in class, but I just wanted to have it here in the video. So if I click element result and hit apply, what I get is a table that lists all of the data associated with the internal element forces in the structure. Now, because this is a truss, everything is zero other than the axial forces, which makes sense. It's a truss. There's only axial forces. What you will find is that for every element, there's a pair of numbers, one at the beginning node and one at the ending node, and they're always going to be of equal magnitude and opposite direction. Now, if you recall in matrix analysis, we always adopt a consistent sign convention, and so if we're talking about a given element, um, so in where it says here, where it says refer to local coordinates, we can sort of idealize the element as just sort of sitting flat. We're not getting too far into matrix analysis land, but for the sake of discussion, we can just assume that we have a flat element just laying, let's say, on a table. And so for element one, the first force is negative and the second force is positive. So if you think about an element and picture an element in your head, the force on the left side of the element is negative, so that's got to be going to the left. And for the force on the right, it's positive, so it's got to be going to the right. So if you think about that, if you have an element, what scenario do you have a force on the left side of the element that's going this way, and then on the right side that's going this way? Well, that's tension. Okay, so this first element is in tension. Now, if we talk about, let's say, I don't know, the last element, okay, here's the last element. The force on the first node is going to the right, and the second node is going to the left. That's doing this. That's compression. So a quick shortcut, if you want, is you can always just look at the second number, and if the second number is positive, that element is in tension. Okay. Now, in order to turn this into usable data with Excel, there's a couple of things you can do. One of the things I didn't mention is that, let me clear the text. If you look here in the bottom menu right here, we can click element results. We can also see where it says delimited by, and it has these vertical bars. We can hit apply, and now you can see the tables have these vertical bars there, and you can take that and copy and paste it into Excel, or you can use the text to columns approach. So let me clear all this. Let's do what we did in class. So just create a report here. I'm going to save the text. I'm going to put it on the desktop, and we'll call this just report. Okay. We'll minimize this, and then we will open Excel. So here I have a blank Excel document. Okay. And I will open this report. This is in Notepad. We'll just highlight it all with Control A, hit Control C, go to Excel, hit Control V, and there we go. Now let me minimize this. Okay, so here's the the table pasted into Excel, but I can't really do anything with it. Like I can't say equals that plus 3. It doesn't understand because Excel pulled in this data as text. It did not pull it in as actual numerical values. I need to take this and convert it into something I can actually do computations with. So what I'm going to do is I'm just going to highlight the table I care about. That's just this table right here. You could do it for the whole thing, but I'm just going to do it for this table. And I'm going to go up here on the very top to the Data tab. And over here near the middle, there is a command called Text to Columns. And so what this is doing in Excel is it takes textual data and it will deposit that text into various columns dependent upon how your data is organized. So it will allow you to take text data and turn it into numerical values that you can form computations with. And there's a little wizard that guides you through the steps. There's a couple of ways to do that. We can either do delimited or fixed width. And I think that's going to be contingent on how your table is set up. To me, I kind of like delimited because at least with these Mastan reports, all of the data is separated essentially by spaces. That might mess your title up at the top, but that doesn't really matter. Um, Now you can see once I check or uncheck the space, you can see here once I check the space, Excel's figuring out, okay, this is where this data goes. I can hit finish, and there you go. Now you can see that it's already been organized into tables. What I'm going to do also, just to make it a little easier to see, I'm going to go, instead of turning them into scientific notation, I'll just turn it into general, and there you go. So if I zoom in a little bit right here, you can see now I've got each of my members figured out. And what I can do is I can just say, okay, give me just the second value, and boom. So there's element 1, element 2, element 3, element 4, element 5, element 6, element 7. And so we have tension, tension, compression, compression, tension, tension, compression. Pretty straightforward. So it'll allow you to do your project calculations really easily. Again, I'm totally fine with you using Mastan to perform your structural analysis. Okay, so with that, let's go ahead and get into our presentation. So what we're going to be doing is looking at um, our second example in Mastan. And essentially what we're trying to do in this example is explore some additional features that we didn't utilize in the first. So for example, in the first example, we were looking at a truss. Now we're looking at a beam or a frame or flexural element. In the last example, we had members that were applied or loads that were applied only at the joints. Now that's not going to be the case here. We're going to have concentrated moments. We're going to have fixed supports, internal hinges, custom sections, everything basically that we didn't cover in the first example to do linear analysis. Now, again, just to make sure everybody's familiar with how Mastan works, we have basically our menus up top that pull up command features that we enter into the data entry toolbar down below. And we just start from the left, work our way over, and once we're done, we hit go. We post-process our results, and it's pretty straightforward. Now, I want to pull up the example that we're going to do today, which is going to be this example. What I'm going to do is I'm going to use a little bit of the tile feature in Windows 11 to pull a lot of this stuff all into one window so it's a little easier to see. But to talk a little bit about the example, so here's the example that we're going to do. First off, we have 0.9 kips per foot distributed load on a couple members. We have a concentrated moment. We also have an internal hinge. We have fixed support. So there's a lot here that we didn't cover before. Okay. Now, below this image, I have the analytical model present for the beam. And if you'll notice here, there's sort of this green circle that shows up right there. That green circle is the way that we're going to model the internal hinge. So we're going to go through that in sequence, and you'll kind of see how this works. Okay, so let's go ahead and let's see if I can pull some things up to organize the screen a little better, because I kind of want to make sure that we're seeing everything all together. So I'm going to put this up here. I'm going to put, let's see, let's put, escape from that. Let's take Mastan, clear the text, cancel. Let's go File, New, start over. Yes, we'll put a our Mastan window up here, and then maybe we'll put our lecture notes here. So let's do that. There we go. I think that's going to be pretty good. That way we can kind of see everything as we're modeling it. Okay, so what we're going to do is, so I have the, let me go up here and keep this up. So my idea is that as we're going through this, the beam that we're modeling is always going to be up here in the top left, and then we can go through the slides here in the bottom left, and then Mastan will be up here in the top right. Okay, so what we're going to do is we're going to go through the geometry, and defining the geometry is going to be very similar to how we did this before. We're going to define nodes and elements, and you can see I've got the nodal coordinates right here, pretty straightforward. So we'll go to geometry, we'll go to, geometry, define nodes, and then we will go in. Let me see if I can take this. Oops, sorry, that's not what I wanted to do. See if I can take Mastan and make it a little. Oh, let's see if I can make Mastan maybe a little bigger in some ways. Let's see if I can do that so we can see the data entry. That might be a little better. It was squishing the data entry toolbar down there. I wanted to make sure that was visible. There we go. That's a little better. Okay. So let's go ahead and enter our data for the coordinates. So we have 0, 0, 0. Let's apply. We have 16 times 12. Remember, we can do math inside Mastan. We're going to do 32. And we're going to do 48. Apply. And then cancel. So we have our 4 nodes created. Then we're going to go to geometry, define element. So we're going to go from N1 to N2. Apply. N2 to N3. Apply. N3 to N4. Apply. So there's our structure. Again, the structural model is very, very simple. Now we need to define a connection. Okay, now connections are the way that Mastan defines internal releases or internal hinges. Okay, so what we're going to do is we're going to use we're going to go to geometry. We can see there's basically a group of the nodes, a group for the elements, a group this for a frame, and then we can see here where it says define connections. There's 2 connections that are available in Mastan, flexure and torsion. We're talking about hinge, so we're going to define flexure. Now what we're going to do is we're going to click one of the elements. So let's click element 1. And what we're going to do is we're going to make one of the elements pinned. So we have rigid, pinned, and semi-rigid. So if we wanted to make it somewhat flexible, we're just going to go ahead and do pinned and hit apply. And you can see there's the hinge that's been placed. Now, the big thing is when you're modeling hinges, don't release both ends, release one or the other, because you can create an unstable model. It doesn't really matter which one that you do, as long as you model the hinge, you'll get essentially the correct answer. Just make sure you're not doing both. Okay, so we went through and defined the connection, pretty straightforward. And here's what your geometry should look like. Again, I think the geometry was really, really simple. Now we're going to get into defining properties. The material is going to be defined exactly as it was before. The section's going to be a little different. Okay. Now for let's do the section first. So let's go to geometry, or sorry, go to properties, define section. Now, last time what we did is we used the values that were in this database. Okay. We can't really do that here. Let me hit cancel because we're not using one of the stock shapes for this problem. We were just told that I is 15,000, so we have to define one. Okay, so I'm going to define a new section, and I don't remember what I had everybody call it in this. I think custom 1. Okay, so we'll name it custom 1. And we need to define the section properties. Okay. Now we're told for this problem that I is 15,000. Okay. So what we're going to do is we're going to change our moment of inertia to 15,000. And specifically, it's the moment of inertia about the z-axis. Remember, in 3D, if you're bending, your moments are bending about the z-axis. That's why we do IZ. Now, if I create this right now, it's going to get upset at me. And what I mean by that is, in order for Mastan to analyze the structure, you have to fully define properties necessary for your stiffness matrix. And what that means is you need an area. Now, to be frank, the area isn't really going to affect our results, but we have to put something in. So I'm just going to go ahead and put 1. You can put whatever you want in. It's not going to affect your answer. The only time it will affect your answer is if you have loads along the axis. Well, then you need a cross-sectional area to accurately capture that. So let's just hit apply, and then what we'll do is properties, attach section. Or we can just attach it to everything. So now you can see our elements changed a little bit because now they have a property attached. Now we need to define a material. This material, I guess we'll call it concrete because the E value is a little closer to concrete than it is to steel. 4,000. Apply. Properties, attach material. Apply. And there we go. So there's our properties created and attached. Now we need to get into creating the conditions on the model. Now, for this problem, let's talk a little bit about that. So the beam has a fixed support. So let's start off with the fixities. Okay. Now here's the beam over here in the top left. We have a roller support at C. So let's go ahead and do that first. So we go to conditions, fixities. Let's do a roller support at 3. So that's just a Y displacement. Hit apply. And we'll hit cancel just to have that. So there's our roller. But then on N1, we have a fixed support, not a pin, a fix. And a pin support has an X reaction, a Y reaction, and a moment reaction. And so the moment's going to be about the Z axis. Okay. So we go to conditions, define fixities. We're going to go to node 1. Then we're going to do X, Y, and Z rotation over here. And then we hit apply. And there we go. So we can hit cancel there. So one thing you can do, there's a quick little shortcut. If you hit Control F, it will bring everything into zoom. So just a random note there. Okay, now let's now look at our forces. So we have 2 forces that we need to apply. Well, 1 force and 1 moment, I guess I should say. And if we look here at joint D, okay, so let's go to conditions, define forces. We're going to go to N4 and define a -40 right here, and then go to conditions, define moments. We're going to go to N4. Now in Mastan, counterclockwise moments are positive, so this is going to be a negative moment, and it's -200 in the problem statement, but it's 200 foot kips. Remember, in Mastan, you must use a consistent unit system, and we're using inches, so we need to multiply that by 12. Okay, so we hit apply, and now you can see the moment. I'll hit Control F to sort of bring that back in. Okay, so now we can see we've got our applied moment. We've got our transverse load at node 4. The only thing left is our distributed load. Okay, now in Mastan, we go to define uniform loads. That's what a distributed load is. We're going to do this on elements 1 and 2, according to our problem statement, and it's -0.9 over 12. Okay, and the reason why it's over 12 is because, again, kips per foot versus kips per inch. Now, one thing I really didn't get too far into, and it doesn't affect beam analysis at all, are these input references. So local versus global coordinates, essentially, in a nutshell, we're talking about whether or not the loads are aligned with the coordinate system over here, or if they're aligned along the axis of a member. So for example, if you have a member that's angled like this, do you want a vertical load to go up and down like this, or do you want it to go along the axis of the member? That's what local versus global means. But since the beams are flat, they're essentially the same, so it doesn't really matter. So we hit apply, cancel, and there we go. And now if you look, our model's done. I mean, we've got our geometry defined, all the properties defined, all the loads defined, the fixities defined. We're good to go. So we just go to analysis, first order elastic. We make sure that we're using the right one. We're using a planar frame, apply, and we're done. So we can look at some really cool stuff here. So let me just take a look at a couple things that we can do. Now, first off, I will save. Always a good thing to do. So we will save that as example 31. I actually did forget to define a title here. It's not all that necessary, but it does. Example. I think I said example problem. I said example. All right. So we do need to. So the reason why we create the title is that when we say, "Okay, give me the reactions," and we hit apply, we can see that that shows up here in the report. Here you can see our reactions. This is RX and RY for our supports, and here's our moment reactions. So um, pretty straightforward there. We can look that up pretty easily. We can also go through and let's go to results, node displacements, for example. So if we go here into results and we go to node displacements, we can actually like just click that. There's our displacements. Obviously, no displacements there. Get displacements here, displacements here, displacements here. Now, if I go to File, Create Report, let's clear the text. Let's go to Clear Text. Let's go to Element Results. I think I talked about this a little last time. So if you do this, you will find results on the either end of each element. To be honest, these results don't, I don't want to say they don't really mean very much, but a lot of times with shear and moment, you need to look at the whole picture, hence why we plot a shear and moment diagram. But one thing that is kind of cool is you do see, zero moment, at the end, which is kind of cool. We have zero moment versus like 2.16 times 10 to the negative 12. That's just computer rounding and whatnot. But we are getting zero moment at the hinge, which is pretty cool. All right, so if I go to results, let's plot some diagrams. Now, in order to plot these diagrams and make sure that we're kind of seeing what's going on, let's turn some stuff off. Let's turn the node labels off. So I'm going into View Labels. Let's turn the element labels off. Let's go to View Labels. Let's turn the loads off. View Labels. Let's turn the fixities off. And not really all that necessary, but what the heck? Let's turn the connections off. Labels. Turn the connections off. Okay, that's probably enough. So we go to results. Let's go to the shear diagram, for example, and I'm going to fill it. Let's not fill it. Let's not fill it. Let's just hit apply. Here's the shear diagram, but if I fill it and hit apply, now you can see it shaded it in. So that's what the fill command does. But you can kind of see the shear diagram looks exactly what it should look like. But if you really want a good one, results, diagrams, let's look at the moment diagram. Moment Z. There's the moment diagram. Let's fill it. There you go. And look, zero moment at the hinge. Awesome. Exactly what we expect. Let's go to results. Let's look at the deflected shape. Let's make it a scale factor of, let's just leave it 10. Apply. And there we go. If we want to animate it, look at that. Deflecting exactly as it should. Okay. So yeah, this is really cool stuff. At least I think it is. You can see, the models are really straightforward to put together. Not that challenging. Should be a pretty straightforward process to do. If you have any, questions in class, let me know. But again, I'm hoping this homework that's due Friday should be pretty straightforward. With that, that's all I got. I will see you in class tomorrow.